This app blocks a password reset request after 5 attempts from one IP address. Now, I send the same local request with one extra line. X forwarded for 198.51.100.25. The app thinks I am a new client. The counter returns to 1. Change the value again, and it returns to 1 again. Nothing happened to the network connection. Only an untrusted header changed, but the application used that header as identity. In this video, we will fix the trust boundary with 7 local tests. We will cover direct origin requests, trusted proxy allowlists, multi-hop chains, malformed headers, rate limits, password resets, and deployment drift. Everything runs inside an owned fixture. No public target, no real infrastructure, and no just take the first IP shortcut. You need one mental model. Every request has a socket peer, the machine directly connected to your app. If the app is public, that peer may be the user. If the app is behind nginx, a cloud load balancer, a CDN, or a Kubernetes ingress, the peer is usually that proxy. The proxy may add the original client address to X forwarded for, X real IP, the standardized forwarded header, or a provider-specific header. But a browser or script can also send ordinary HTTP headers, so the value becomes trustworthy only when 2 facts are true. First, the request arrived from a proxy you explicitly trust. Second, the header chain matches the topology you designed. If either fact is unknown, the header is data, not identity. Our first fixture is simple: client, edge proxy, app. The second adds a CDN and an ingress. We will keep the socket peer, received header, derived client, and security decision visible on every test. Here is the vulnerable handler. It reads the first value from X forwarded for. If the header is missing, it falls back to the socket address. That looks reasonable in a code review. Behind the intended proxy, the first value often is the original client. Now send 2 requests directly to the app. The first has no forwarded header. The derived address matches the socket peer. The second includes a fake forwarded value. The derived address changes. Test 1 fails because the app accepted proxy metadata from a non-proxy peer. The corrected rule begins with the connection, not the header. Is the socket peer one of the proxies this environment trusts? If no, ignore forwarded identity metadata. Use the peer address or reject the unexpected path, depending on the architecture. If the production app should never be reachable directly, block the origin at the network layer as well. But still keep this application test. Network rules drift, debug routes appear, and staging assumptions leak into production. Defense in depth means the direct path is blocked and the app refuses to trust it. Trust proxy is not a complete policy. Which proxy? In which environment? From which network? With how many hops? In the fixture, the edge proxy uses the documentation range 102.24. The app trusts that range and nothing else. Request A arrives from the edge. The edge overwrites or constructs the forwarded chain according to our policy. The app may derive the client address. Request B arrives from an invented address outside the trusted range. It includes the same header. The app ignores it. Request C arrives from the trusted proxy, but the proxy configuration is wrong and preserves a client-controlled value without a safe append or overwrite rule. This test must also fail because application trust and proxy behavior are one system. The exact allow list might be static addresses, a private subnet, a local socket, a load balancer range, or verified platform metadata. The right answer depends on the deployment. The unsafe answer is a global switch with no documented network assumption. Write the assumption next to the test. Only this ingress can reach the app, and only this ingress supplies the client chain. Now the setting can be reviewed against reality. Suppose the app receives 198.51.100.25, 192.02 opt-in. Which value is the client? You cannot answer from position alone. You answer from the trusted path. Start with the socket peer, the hop connected to the app. If that peer is trusted, move one address outward through the chain. Continue while the address is a proxy you trust. The first address outside the trusted proxy set is the derived client for this topology. This is often described as walking right to left, from the application toward the network edge. Why not always take the leftmost value? Because a client may have supplied an earlier value before a proxy appended anything. Why not always take the rightmost value? Because the rightmost address may be the last proxy, not the user. The algorithm and the proxy's append or overwrite behavior must agree. Our test creates 3 chains: a normal client and edge, a client-supplied prefix followed by the edge, and an unexpected extra proxy. The expected derived address is locked for each case. If the library returns a different answer, do not patch the array index. Fix the trust model. Now add a CDN and an ingress. Client, CDN, ingress, app. At each hop, record 5 values. Who connected to this component? What forwarding header did it receive? Did it overwrite, append, or preserve the header? What did it send downstream? Which upstream addresses does the next component trust? This table exposes dangerous ambiguity. Maybe the CDN overwrites any client provided X forwarded for, then the ingress appends the CDN address. Good, if the app trusts the ingress and the documented CDN range. Maybe both layers append to whatever arrived. Now the left side can contain attacker-controlled data. Maybe staging has 1 proxy, while production has 2. A framework configured with a numeric hop count can derive different clients when a shorter route exists, test the exact production path, the exact staging path, and any health check or internal route that reaches the same app. If paths have different lengths, a single trust 2 hops assumption can be wrong. The goal is not to memorize one header order. The goal is to assign ownership to every hop and make unexpected topology fail visibly. Real traffic is messy. Security code must be boring under messy input. Our 5th group includes a missing header, an empty header, white space, duplicate header lines, too many comma-separated values, an invalid address, an IPv4 address with a port, a valid IPv6 address, and a conflicting xreal IP. The expected behavior is explicit. Missing is not an error when a direct path is allowed. It means use the socket peer. Malformed is never a reason to guess. Duplicate or oversized chains should be rejected, ignored, or handled by a documented library policy, not split with an unbounded custom string function. IPv6 must be parsed as an address, not broken at the first colon. Conflicting headers need one authoritative source based on the proxy contract. Do not select whichever value looks public, and log the failure safely. Record that forwarded identity was invalid, the trusted peer that sent it, and a bounded representation of the condition. Do not copy an unlimited attacker-controlled header into logs. Run these cases through the same function used by rate limits and security events, not a separate demo parser. Fixing the displayed IP is not enough. Find every place the application uses it. Rate limiting is the obvious one. Our local counter should group repeated requests by the verified derived client. A fake prefix must not create a fresh bucket. Password reset is more sensitive. IP can be one risk signal, but it cannot prove who owns an account. Reset links, verified channels, session state, and server-side authorization still matter. Admin access is stricter. Allow this IP can be one network control, but an HTTP header alone must never grant a role. Audit trails need both values, the socket peer and the verified derived client, plus the proxy path or decision reason. If an incident happens, you need to know what the app observed and why it trusted it. Fraud or abuse rules should expect shared networks, carrier NAT, VPNs, IPv6 privacy addresses, and changing mobile connections. IP is a useful signal. It is a weak person identifier. The 6th test runs one fake header through 4 consumers: rate limit, reset risk score, admin gate, and audit event. The correct implementation never lets an unverified value bypass a limit, reduce risk, grant access, or overwrite the evidence. The code can be correct while the deployment makes its assumptions false. Create an integration test that runs after deployment. From the approved edge path, send a request with a known synthetic client marker. Verify the app sees the expected trusted peer and derived client. From a direct internal path, send a request with a fake forwarding header. Verify the app ignores it or the route is unreachable. Add an unexpected hop. Verify the chain does not silently shift the client. Remove a trusted hop. Verify the request fails closed instead of trusting a new position. Then compare the runtime topology to the documented table. This catches changes such as a new CDN, a replaced ingress, a public origin, a serverless preview route, a local development flag enabled in production, or a provider header renamed without the app changing. Run the test when proxy configuration changes, when the platform changes, and before a sensitive control starts depending on the derived address. A unit test proves your parser. A deployment test proves the parser's assumptions are still true. Most frameworks have a setting for trusted proxies. Use the maintained implementation when it matches your topology, but read what the setting means. A Boolean may trust every upstream hop. A number may trust a fixed distance from the app. An address list may walk through known networks. A callback may decide trust per address. Those choices are not interchangeable. On the proxy side, distinguish append from overwrite. Appending preserves the chain and adds the current peer. Overwriting discards client-supplied history and starts a controlled chain. Either can be correct in a designed system. Mixing assumptions is the problem. Also check provider-specific headers. A CDN may supply a dedicated connecting IP header, but it is trustworthy only when the request actually came through that CDN and the origin cannot be reached around it. Do not paste a configuration block from a tutorial and call the boundary solved. Write the path, trusted senders, header contract, parsing rule, and tests in the same change. The final matrix has 7 rows and 5 evidence columns. Expected path, observed socket peer, received forwarded chain, derived client. Security decision. The build passes only if every consumer uses the same verified result, and every unexpected path fails according to policy. Ship when direct origin spoofing fails, only known proxies are trusted, multi-hop parsing matches the documented path, malformed input is deterministic, sensitive controls do not treat IP as identity, and the deployed environment passes the regression test. Stop when the app trusts any sender, chooses a header position without topology, has multiple controls parsing addresses differently, or cannot prove that the public origin is protected. Unknown is not a pass. If the team cannot state who sends the header and who can reach the origin, keep the IP-derived decision out of sensitive authorization. The final rule is simple. Trust the network path first. Then interpret the header, not the other way around. X forwarded for is useful. It is not authenticated merely because a proxy usually writes it. Add these 7 tests to your deployment suite. Direct origin, proxy allowlist, trusted sidechain parsing, multi-hop ownership, malformed input, real security consumers, and deployment drift. If you want a stack-specific follow-up, comment your path. Cloudflare to Nginx, AWS load balancer to Express, Kubernetes ingress to Node, or something else. The next video can turn one documented topology into a complete local fixture. Subscribe to Build Without Blind Spots if you want the tests that sit between the demo works and the system is safe to ship.